Okay, so let's take a look at these applications of exponential functions. So in this problem, they're talking about a radioisotope, and it's a little bit misleading because the name of the radioisotope has a number in it, but that's actually just the name of the item. It's not a value that you're going to use. So this number 99 has nothing really to do with the formula. So the formula asks you to find the number of milligrams, etc., that are left in a radioisotope after the initial value has gone through some iterations of half-lives. So the problem is, in order to use this formula, you need to know either the decay constant, the time, or the initial value. And we only know one of those things, and that is the time, that it has a half-life of 6 hours. So we don't know the initial value, and we don't know the decay constant, which is actually what we're asked to find. So if you do not have an initial value, but you do know that it has a half-life of 6 hours, then you can actually use some common sense to come up with some numbers here. Because if you choose a pretend value, let's say, then you would be able to figure out what the half-life of it is. So let's say I pretend that I have 100 milligrams. Well, after one iteration, or 6 hours, I would have half of that left, right? So if my initial value was 100, my ending value would be 50. And if I chose a different value, right, I just chose an example, which was 150. Let's say I chose a starting value of 2,000. Well, the half-life of that is 1,000. So even if I change my starting values, no matter what I pick, when I divide both sides by this coefficient, right, so if I divide both sides by 100, I'm going to get 1/2 over here. Right? So even if I started with, let's say, 48 grams, well, half of that would be 24. And 24 divided by 48 is also 0.5. And even if I started with 5,000, well, half of that would be 2,500. And 2,500 divided by 5,000 will always be 0.5. So no matter what I start with, my value is going to be half when I'm finished. So I don't even need to know the start value. I can not even put anything in there. And I always know the outcome will be half. So that's where I'm getting this sentence from. Now to isolate my decay constant, I simply take the natural log of both sides, right? Natural log of 0.5 is equal to -6 times k of the natural log of v. So I'm crossing this value out now only because the natural log of v is equal to 1. So I don't need to show that I'm dividing both sides by 1, so I'm simply just going to ignore this for now. I'm going to divide both sides by -6 to get my constant of decay variable by itself. I'm going to use my calculator, and I get this long value here. So depending on what you round to, you would get 0.116. Now if you want to be more accurate, I would use this entire value for k for any further questions, but I'm going to round to 0.116. So now I'm ready to move on to question B. So if I want to determine the amount of a 250 milligram dose after 24 hours, right, then 24 is my time, 250 is my initial value, and my constant decay is 0.116. So we simply place those values into the formula. Now remember, this is just a title. The number, or the amount, after 24 hours is equal to my initial value times e to the -0.116 times 24. So I'm just simply going to put that into my calculator, right? 250 times e raised up to the -0.116 times 24, and I would get 15.447, etc., etc. So approximately 15.5 milligrams, depending on what you're asked to round to. So this is just a simple evaluation. Remember, this is a title. It's not part of the solving process. All right, let's take a look at the next question. So in the next question here, let's see, I'll cover up some of this as we're starting. The herd of caribou, right, has an initial value of 4,700, so that goes here. It has an ending value of 472,000, which goes over here, right? The population after a length of time. And then I need to figure out what that time is. So 1954 to 1984 is 30 years. And now I can solve for k by dividing by my coefficient and taking the natural log of both sides here, right? So if I divide both sides by 4,700, I'm going to get this value, which is pretty long. I know I'm keeping it really long, but when you round here in the middle and then you round again at the end, you get farther and farther away from the actual value. So now when I take the natural log of both sides, remember I can ignore this, right? This is a 1, so I'm not going to show that I'm dividing by the natural log of e because it's really not necessary. So I divide both sides by 30, and I get my k value, which is approximately 0.154, depending on what you round to. So if you rounded slightly different or you kept it longer, your answer for part B might be slightly different than mine. Alright, so if I want to find the population in 2010, then I need to know how far 2010 is from my initial 0 value of 1954, right? So that's 56 years later. So I'm just going to fill in that formula, right? The population after 56 years is equal to my initial population raised up to my constant growth factor and the length of time. Remember, this is not a value, it's just a title. Put this in your calculator, and I think depending on what you round to, it should be approximately 26.1 million. You might have a slightly different number here if you used a different value than 0.154. Alright, question 15. Population of rabbits doubles every 60 days. So in this problem here, they give us this formula. So if you're starting with 10 rabbits and it doubles, then that's where you're getting the 2 from, and the time is per 60 days. So if the population is 320, that will take the place of p. Divide both sides by 10. And then there's actually 2 different ways you could attack this problem. One is to take the logarithm here, right? So if a base of 2 has a power of t to the 60 with an answer of 32, then that means that the log base 2 of 32 would be equal to this power. So I simply use my calculator to find log base 2 of 32, which is 5. And then I multiply both sides by 60, and I get my final answer of 300. And a second way would be to back up for a second and you go back to this initial formula here and think about what if I didn't want to use a logarithm, even though I totally could. And that would be to think about maybe getting like bases, right? So if I have a value and I have another value with a power, then the powers are equal if the bases are equal. So if I can get like bases, that's another method. You don't have to use it, but 2 and 32 do have a relationship because 32 is actually 2 to the 5th power. So now I can just ignore the bases and set the powers equal to each other. So 5 is equal to t over 60, which is the exact same equation I got after I used my log base 2 of 32. Multiply both sides by 60, and I get the same answer. So 2 different methods, doesn't matter which one you use. Okay, and now for that mortgage question. So when I left, we had filled in all these values, and I know I don't have the question on the screen, but the Banks family wanted to spend no more than $720 a month. They were borrowing $120,000 at a rate of 4.8%. So we filled in all those values. Then we multiplied these two products here to get, we reduced these fractions here. Then we multiplied these two products here, and we got this green sentence. And then I realized, well, you can't have a variable in the numerator and the denominator, so let's clear the denominator. So in order to clear a denominator, you multiply both sides, right? Oh, I cleared my 480, right? Divide by 480. And I multiplied both sides, so let me go back a second here, right? Okay. Here, if I multiply both sides by 1 over 480, which is what I'm doing here. I'm writing it as dividing by 480, but I'm multiplying both sides of my equation by 1 over 480, and that's giving me a cancellation on the right and a new value on the left. So I have 1.5 here in green, and then on my right I'm left with this. And my next step after this green step was to multiply both sides by the entire denominator, right? Giving me a nice cancellation over here. And then a distributing problem over here. So I can't multiply 1.5 times this value, but I can show that they should be multiplying. So that's how I got this. 1.5 times the quantity 1.004 to the nth power. And then 1.5 times minus 1, which gives me this. And over on the right hand side, I was left with just this exponential expression here. And then I realized, well, I can't solve for n unless all my n's are on the same side. So we decide to move this 1.5 to the right, making it positive, and move this 1.004 to the nth power to the left, making it negative. And then I realized, well, if I have two variables, I have to have only one. And since their bases match, I can actually factor that out. So if I factor out 1.004 to the nth power, then I'm left with this, right? And I'm left with this and the invisible 1 that I would get here, right? So if I'm dividing both of these terms by 1.005 to the nth, then I'm factoring that out. This is my remainder, and a minus 1 is also my remainder. So you see what I'm, well, loosely speaking. So that's where this is coming from. If I take this value away, then a placeholder 1 goes in its place. And if I'm factoring out this here, then 1.5 remains in place. So this is what I factored out, and this is what was left. This is something I can simplify. So 1.5 minus 1 is 0.5. Now, all I need to do is get rid of this 0.5, and then I can deal with the power. So I divide both sides by 0.5, and I get 1.004n is equal to 3. Then I take the log of both sides, right? So n log 1.004 is equal to the log of 3. So I'm going to clear this out and get my final answer here, that the number of months, right, this is in months, is 275.2. The question asked how many whole years. How many whole years? So I'm going to divide by 12, and that's going to give me approximately 22.9 or 23 years. And that's how you solve that mortgage question.